Okay, so welcome to another video. And this one we're continuing on looking at the properties of solutions and specifically looking here at what happens to the vapor pressure of a solvent when we add a non-volatile, non-electrolyte compound to a solution. So those two words are very important: non-volatile, non-electrolyte. So in other words, something like, for example, not sodium chloride or not a gas. So something like glycerin, or in other words, something that does not conduct electricity, or something that in itself cannot have a vapor pressure. So um, let's read the question. It basically says we have glycerin. It's a non-volatile, non-electrolyte with a certain density at a certain temperature. Determine the vapor pressure of a 25 degrees Celsius solution made by adding 50 milliliter of glycerin to 500 milliliter of water. The vapor pressure of pure water at 25 degrees Celsius is a specific pressure, and its density is 1 gram per milliliter. Okay, so let's think about what's happening here. Our starting situation is where we only have water. So let's draw a little thing where we cap off our water beaker. So our water beaker is, filled with water. So here we have 500 milliliters. So we have 500 moles of water. And when you close a beaker and you have a liquid like water that can which is able to go into its vapor phase at this temperature. So in other words, it's not at a temperature where it will freeze. It will go into its vapor phase. So there's going to be some water vapor floating around here. Right. And this water vapor, when it's just water in this beaker, has a standard vapor pressure. So the vapor pressure of water is equal to this 23.8 torr. Right. That's easy enough to understand. And of course, this is importantly at 25 degrees Celsius. This is all specifically at 25 degrees Celsius. This is the information. Then what happens is we say, well, right, now we want to add 50 milliliters. So we add 50 moles or 50.0 milliliter of, what's it, glycerin or glycerin. And how does that affect our system? So we still have a little capped system, a little closed system. The temperature doesn't change, still at 25 degrees Celsius, 25 degrees C. Its temperature or its volume is, of course, going to increase slightly. So all that you have now is you have a total volume of 550.0 milliliter, or roughly, but that doesn't, not too important. But the important part is you now have water plus glycerin here at the bottom. And glycerin is not volatile, it's non-electrolyte, so it's only going to be dissolved in the water. It's just floating around in the water, it's coordinating there in somewhere. But the important thing is glycerin is going to have some effect here on the vapor pressure of water. Right, because firstly, it's decreased the amount of headspace, and secondly, it's wanting to interact with some of the vapor phase. It's interacting with the water in some kind of positive or negative, or mainly positive. If it's an ideal solution, it's a positive way. It takes away some of the vapor phase, and hence what happens is we now will have a new vapor pressure. So essentially just the vapor pressure of our water changes, and we expect it to be lower. And by what does it lower? it lowers by the fraction of what the water becomes. So essentially, if the water made up 100% before the glycerin was added, if the water now makes up 50% of the mixture, mole-wise, so you'll see we use the mole fraction, but mole-wise, then it will have 50% of its um, vapor pressure left over afterwards. So what we'll use is Raoult's law, which says the vapor pressure of the solvent is equal to the mole fraction of the solvent multiplied by what the standards, in other words, if there's no mixture, so just at that temperature, for that volume, for all those conditions, what that standard vapor pressure of that solvent would have been. Right, and that kind of makes sense. So you had so much water that was made up 100%. Now the water is a bit less, so its vapor pressure should decrease by that amount. And the reasons for that is more chemically based. I mean, there's new interactions being introduced. There's hydrogen bonding. There's other molecular interactions that might, I mean, glycerin specifically is hydrogen bonding, but with water, but there might be some other reasons creating, reducing the headspace, creating molecular interactions, causing less vapor phase, and hence decreasing the vapor pressure, given that it's an ideal solution. But that's all. That's the general idea of Raoult's law and what we'll assume. So what do we need? We have the vapor pressure of the standard vapor pressure at this temperature. So we just basically need the mole fraction, and then we'll be ready to go. So we need to calculate the mole fraction of water, the mole fraction, number of moles of water, and we need to calculate the number of moles of glycerin. So I mean, that's mass of water divided by molar mass of water. Mass of water in this case, we're not told directly the mass, but we're given the volume and the density. So that's volume of water multiplied by the density of water divided by, still divided by molar mass, interesting M there, but molar mass of water. 500, 1, and about 18 should give you a value of 27.8 mole water. Same with glycerin, because it's the mass of glycerin divided by the molar mass of glycerin. It's equal to, we're again given the volume and we're given the density of glycerin. Divide that by the molar mass of glycerin. Volume glycerin is 50 moles. Density is 1.26. Molar mass of glycerin, you can calculate, you're given the molecular formula. So it's 0.68 mole C3H8O3. Right, so now we have the number of moles. We can calculate the mole fraction of water, which will be the number of moles of water divided by the total number of moles, which is total number of water moles plus the number of moles of glycerin. And you should see water completely dominates, which makes sense. And therefore, the vapor pressure of water in the mixture, or after the mixing, is equal to the mole fraction of water multiplied by the vapor pressure of water without when there's no mixing or when there's, yeah, so it's 0.976 and the 23.8 torr. You see it's 23.2 torr. It's not too massive of an effect, but still an effect. Doesn't specify what unit, but then you can leave it in the unit as given. There is another way to do it. You can go the route where, so let's say okay, so essentially we see there's a drop in vapor pressure. Why? There's some molecular interactions, there's a reduction in headspace, which you would think would increase the pressure, but actually it doesn't. It reduces it. And how we calculate that is Rahul's law, which is the new vapor pressure is equal to the mole fraction of the solvent multiplied by the standard vapor pressure of the solvent at the temperature which the mixture is. Something else that you can do, so you can do, always get a shock when it's that thin. So you can tell yourself, or you can calculate the change in pressure or vapor pressure of the solvent should be equal to minus the mole fraction of the solute multiplied by the vapor pressure of the standard vapor pressure of the solvent at the temperature. Which also makes sense because if it depends on what the percentage or how much solute you add, what the effect will be on the solvent vapor pressure, so what that change is then going to be. So you can just quickly go and check for yourself. The mole fraction of glycerin is going to be 0.024 about, and that means the change in P of water, or the vapor pressure of water, is going to be equal to minus that of glycerin, water minus 0.024, 23.8 torr, gives us minus 0.571 torr, and hence we know that the change in vapor pressure should be equal to the new vapor pressure, so the vapor pressure after mixing, minus the vapor pressure before mixing, which will be the standard vapor pressure. So that's what we wrote on top here. The standard one and the new one. So therefore, if you solve that for sort of new vapor pressure, then it would be the change in P water plus the standard vapor pressure it's minus 0.571 torr plus 23.8 torr, giving us 23.2 torr. Right. So those are the two ways using Rahul's law. Basic idea, you have a vapor pressure, add something, vapor pressure reduces. By how much does it reduce? Depends on the mole fraction of the solvent, or after the mixing. Okay. Thank you for watching. I'll see you in the next video.